In this video, we're finally going to start talking about reactions. And you're going to get introduced to the first type of reaction, which is called an addition reaction. Alkanes, we saw, are not very reactive. They have very stable sigma bonds. But when we get introduced to alkenes and alkynes, we then start talking about the nature of a pi bond versus a sigma bond, and we see that pi bonds are weaker than sigma bonds, which means that they are more reactive, and therefore they react with many different things. And we're going to see a variety of things they'll react with, but the first type of reaction we're going to look at is the reaction of pi bonds with proton donors or acids. Right? So if I take an alkene and I react it with HX, where HX is an acid. So when we're first being introduced, X is going to be a halogen, so HBr or HCl. And notice I'm highlighting the pi bond of that alkene. And of course, I could be using an alkyne as well, where I'd have two pi bonds, and we'll see the difference between them. But for now, as an introduction, we see a pi bond reacts with HX, and the result is I get a carbon-hydrogen bond and a carbon-halogen bond. So what happened in that reaction? Well, notice an HX sigma bond is broken, and an alkene or alkyne pi bond is broken in the process. So we're breaking one HX sigma bond and we're breaking a pi bond. But we're forming two new sigma bonds, a carbon-hydrogen sigma bond and a carbon-halogen sigma bond. Okay? This is called an addition reaction because we have added hydrogen and the halogen to the organic compound, which in this particular case is an alkene. So we're adding atoms to the basic framework of our organic compound. And when that happens, it's called an addition reaction. We're going to see many types of addition reactions, so it's important to understand and distinguish the types of reactions, right? An addition reaction. We'll see substitution reactions, we'll see elimination reactions. So this is an addition reaction. Now, one of the questions often asked is why do HCl or HBr donate a proton to the alkene? And this is going to be a fundamental understanding of how the reaction takes place. So the first thing that we have to do is we have to remember that in an HCl or HBr bond, electrons are not shared equally between the two different atoms, right? We talk in general chemistry about the electronegativity difference between hydrogen and chlorine. And so we say, okay, if I have a HCl bond, the chlorine is more electronegative than the hydrogen, and therefore I have a dipole moment where electrons are residing more on at the chlorine nucleus than at the hydrogen nucleus. Well, how does this play out in our idea of molecular orbital theory? So far, we've looked at two atomic orbitals mixing where the atomic orbitals, the initial atomic orbitals, are at relatively same energy levels. When we think about how hydrogen bonds to chlorine, we have to think about how the atomic orbitals are going to mix. So of course hydrogen has its 1s orbital. And when we think about chlorine, chlorine has 7 valence electrons in the n equals 3 level, right? And therefore we have the 3 p orbitals and the 1 s orbital, 3s orbital and the 3p orbitals. And notice where I'm putting the energy level. So it's important to recognize where the energy level is. It happens based on calculations, mathematical calculations, which is all we need to know, that the 3p orbitals are they're actually a lower energy level than the 1s orbital. Now that is important, and the reason, the way we determine this is actually based on ionization potentials. Um, so it's actually harder to ionize a 3p than it is to ionize a 1s electron of hydrogen. So if I think about where electrons reside, I know there's an electron in the s orbital, and there are 7 electrons, valence electrons of chlorine. So there's 2 electrons in the 3s, and then there's 5 electrons in the 3p orbitals. So it looks like this, right? We have looked at this energy, or this electron configuration in general chemistry all over the place. Well, now we're going to see how they mix together. And if you think about the 3px and the 3py, they're filled already. So what's going to happen is that 3pz orbital has the 1 electron available to it. It is going to mix, and it alone is going to mix with the 1s orbital. Notice the 3s orbital, while it has correct symmetry, it's too different apart in energy. The 3pz orbital has less symmetry to the 1s, but it has about the same energy level. And as a matter of fact, it's a little bit lower in energy. So when they mix, what do we end up getting? Well, how many orbitals are we mixing? 1 orbital from the hydrogen 1s, and then 4 orbitals from chlorine. So we need to end up with 5 new orbitals. So we get one of the orbitals is simply from the 3s, it's called a non-bonding orbital, right? And then we get a new orbital from the mixing of the 1s and the 3pz, and that's going to be our new sigma bonding orbital. And of course the 3px and 3py are filled, and so they don't contribute, and so they are simply there as non-bonding orbitals. And finally we have a sigma star orbital. So notice I have 1, 2, 3, 4, 5 molecular orbitals. I start with 5 atomic orbitals, I end with 5 molecular orbitals. Okay, so now I'm going to fill the electrons. I start with the non-bonding electron, right? And then I fill the sigma bond with 2 electrons, and now I have 4 electrons left, and they go into the non-bonding electrons. And this is where, notice chlorine, we typically show, three pairs of electrons around chlorine. That's from the non-bonding pairs of electrons. So we have 3 non-bonding pairs, and now we have a sigma bond. We also have a sigma star bond, and it is higher in energy. So this would be the lowest unoccupied orbital. This is the lowest unoccupied orbital of HCl. That's going to become important later on in terms of reactivity. The sigma star is the LUMO. Now, another important facet to understand about this molecular orbital, this new molecular orbital, is that the energy level of the electrons in our new sigma orbital is actually closer to the energy of the chlorine atom itself upon mixing. What this means is that there is more electron density that resides on the chlorine, which we already know based on what we learn in general chemistry about electronegativity differences. But it really plays out in terms of molecular orbital. We see that that sigma bond has more electron density that resides closer to the chlorine than the hydrogen. We also see the sigma star is aligned more in energy with the hydrogen atom. And that's also going to become important later on. And so we get a picture, our molecular orbital picture of that sigma bond is actually kind of skewed. And so notice I'm showing that lobe between the 1s and the pz is skewed. There's more electron density on the chlorine than there is at the hydrogen. And that's kind of going to be my representation of that. The key is to understand there's more electron density at the chlorine, less electron density at the hydrogen. And so we get that separation of charge. And our molecular orbital picture um, comes into play when we talk about reactivity, but it also reinforces the idea of that dipole between hydrogen and chlorine.